Okay, I've come to you now with nothing here except for a blank screen, so we can talk about some of the kind of last inputs to when we're doing these problems using a matrix format. So I'm going to go ahead and sketch something here and try to use some of these kind of tools with the color as well. So I'm going to go ahead and draft. I'll draft in black my basic structure. So my basic structure, I'm just going to go ahead and draft the structure here. That is. Okay. Try to do a little bit of sketching here. My daughter's trying to teach me. Got a structure out here, and it's got a framed moment there connection, so something that makes it good and tight right here. Right, so that's my forces. It is a pin joint on the ground. All right, so it's a pin joint on the ground. It has, let's go with the pens, it has a applied force of, we'll make the forces applied green, and it's a force that looks something like that. Of course, there could be any other set of forms. I'm just going to leave it as one force right now, and it has then a reaction here. Once again, change the color for the reaction here. A reaction of a known direction from a known point, and usually that known direction is because you know the locations of those 2 points. So you've got a reaction there. Obviously, you got a reaction there and a reaction there. And of course, you can then describe these points here as, if you call this force 1, we're going to call this reaction at A. Reaction at A. We'll call this force 10, since we're doing a lot of these in CAD anyway, and we're starting counting at 10, and force 11. Of course, force 10 is really not, going back to my pens here, it's really not a force, it's a reaction. So this becomes a reaction. Reaction at B. Now, reaction at B has a known direction. And the known direction you'll see is what we're talking about here now. All right, so force 11, right, we're going to call this at x sub 11, y sub 11. And it has a magnitude of force, so it has a force of f of x at 11 and f of y of 11. And we're talking about here, of course, knowing this is my 0, 0 point and a right-hand coordinate system. And that'll become obvious. And what I'm going to first do is let's say we know what this direction is here, this theta. Therefore, I can write my radial force pair this way by having, I'm going to call this x2, y2. We're going to have the value of the radial vector there, the value of the radial vector there, and then basically this is going to be the cosine of theta and the sine of theta. These describe the unit force vector. Here, of course, we will have x11, comma y11, and then basically fx11, fy11. So that's the radial force pair. And what I'm mostly talking about right here is the fact that we should really divide that up into two matrices. One which is 1, 0. In other words, 0, 0, and then 1, 0 for the reaction at A in the x, and another one which is 0, 0, 0, 1, the reaction at A in the y, because each of these are the unit vectors. And if we're going to describe our unknowns by a unit vector here and here, it makes it a little bit easier to comprehend when we have a known direction or unit vector there. All right, that said, here is a little piece of knowledge for you, I think. If you think about a path here, a velocity v, right? Let's see, you have a point here and you're right here, and you want to know the moment arm, basically how close something is going to pass to you. All you need to do is write a cross vector of r cross lambda sub v. In other words, what you need to do is do a cross product of your radial vector and the unit vector of the velocity, and that'll get you your intercept distance. Now that's the same thing that we're doing here, more or less. If you take r cross lambda sub force, that gets you the moment arm. And what you of course know in this case, if you're torquing about this point, you have a torque. In this case, this is a negative torque, and so this has to be a positive torque. They have to be equal and opposite. So that sense, what I really wanted to talk about is, once again, point out that probably it is best. I've seen some students do it. I don't know that I've been consistent in it, that if you have a reaction of two directions there, you don't know the mathematical relationship, you write it as two separate radial vector force pairs. If you do know the relationship, you actually write it up this way. All right, so I'm going to post this one out. Start looking at kind of reworking some of these things and letting you know that this format here is equal to, of course, what you could have done, which is r cross f. You could have taken basically the radial cross product there and have it equal to r cross f. So the area basically of this kind of length times distance has to be the area as a length times distance. It's a radial arm ratio problem. It's going to be more because it's closer, and it's going to be that force times the ratio of the two, and it's going to be more. So we go back to that more or less problem. We also continue on to look at that, the more or less. We also want to know positive or negative moments, and we want to use logic. All right, so not much cleaner, but that discussion, particularly in doing this for the rest of the time, and then as you get going on this, it's going to be a 3-vector unit vector system when you've got actually a third coordinate system. In other words, x, y, and z, a third dimension. All right, we'll stop this and post it out and see how it looks. Thanks for listening.